today we'll be looking at actually working out gradients of curves, and we're going to try to find a more accurate way of doing so. So how we actually go about this is we're actually looking at some secants, okay, and then looking at how the patterns in the secants will lead us to the gradient of the tangent. So here's a working example. So what we're actually going to do is we want to find the gradient at this point P here, okay, and that's going to be the 0.11. What we want to do is look at some gradients and then see how close we can get. So what we're going to do is we're going to pick another point on the graph and then work out the gradient, and we're going to keep refining it until we can get close to the gradient at that particular point. So if we look at the first one, we're going to first put Q up here, and we're going to work out the gradient of this particular line. Okay, so we can see that's going to be pretty close. So the gradient of P is going to be about that-ish. Okay, so we're going to have something that looks a little bit close to it. So using those 2 points, we're going to draw out our rise over run and work out our gradient there. So we can either draw it out, or we can use y2 minus y1 equals x over x2 minus x1. So m equals y2 minus y1 over x2 minus x1. So all that gradient stuff we did in the coordinate geometry is quite important. So we could do that. Let me just get rid of that tangent so it's out of the way. And if we go to work out that gradient, we end up with a gradient of 3. Now obviously that's going to be a lot steeper than the actual gradient that I had drawn in before. So what we're going to do is we're going to move Q a little bit closer. So rather than 2, 4, what we're going to do is we're going to move Q so that, let's say, we'll use 1.5, x is 1.5. So we're going to pick this point here. So there's Q. And then so what you can see is this gradient's now a little bit flatter and probably closer to P. So using these two values, we're going to, again, work out the gradient. So there's our triangle. Work out the gradient, rise over run, and we'll end up with a value of 2.5. Okay, so we're sort of getting closer and closer, but it's still not exactly, exactly the gradient at P yet. Okay, so we're getting closer to it. What we can then do is we can move Q again. Okay, so if I move Q, and this time let's make it 1.1. So it's going to be really, really close. So it's going to be right there. So if I put Q there, you can see that secant is going to be very close to the actual gradient of P. So if I go and work out a gradient, rise over run again, I'll end up with a gradient of 2.1. Okay, so it looks like as we get closer, so we started at 3, then it went to 2.5, and then now it's 2.1. It looks like as we get closer and closer, it's actually getting closer to probably the value of 2. And what we want to do is keep bringing that Q closer and closer to P until a point where they actually overlap. Now, we can't really just, talk about that by just saying, oh, it looks like it's getting closer to 2.1. We want to be able to put that into numbers. So rather than talking about actual values for Q, what I can do is I can pick a point Q somewhere so that the distance, horizontal distance between P and Q is h units across. Okay, so that's what we're doing down here. If we make the x-coordinate h units away, then what we can do is we can label Q. The x-coordinate is going to be 1 plus h, okay, because there's your 1 plus h, okay, so the x-coordinate is 1 plus h, and the q-coordinate, because it's on the graph y equals x squared, the y-coordinate is going to be 1 plus h all squared, okay, so if I use some number h, that's what it's going to look like. Using the point P, which was 1, 1, and our new point Q, I can work out the gradient by doing y2 minus y1 over x2 minus x1. So there's y2 minus y1, which is 1, because the coordinate at P is 1, over x2 minus 1 again. So that's what the gradient will look like. If I expand and simplify, the 1's cancel, and then you've got that part left. If I factorize that, then I've got h2 plus h over h, and what we can then do is cancel the h's, and we end up with 2 plus h. Now, as we saw before with q, we wanted to bring q closer and closer to p until it's overlapping it. So what we're actually doing is we're taking this value of h and we're making it smaller and smaller until when h is equal to 0, p and q are going to be overlapping. So what we want to do is make h approach 0. Okay, so that's what this means. As h approaches 0, then if h is getting smaller and smaller and equaling to 0, we can see that the gradient is going to equal to 2, because it will be 2 plus 0, which is 2. So what that means is the gradient at P is going to equal to 2. Now there is a formal way of writing this out, okay, and that's coming up next. So if we look at any function fx, okay, then if I'm looking at any point P, if I have an x coordinate, then I can write the y coordinate as fx. If I have a point Q that's h units away, then we know that the x coordinate is going to be x plus h. The y coordinate is going to be f of x plus h. So this is where all that function notation stuff that we did quite early on is really important, and there's going to be a lot of algebraic manipulation here. So to work out the gradient of PQ, what we're going to do is we're going to work out gradient. So y2 minus y1 over x2 minus x1. You can see in that formula that x's will cancel, so the gradient is f of x plus h minus fx over just h. Now what we can do is we can also incorporate the thing that we did earlier, this part here, as h gets closer to 0. So you can see if I make h closer to 0 here, then I'm actually trying to make that bottom bit equal to 0, but we can't divide by 0. So what we'll need to do before we can do that is we're going to have to algebraically manipulate this so that we can cancel the h out. So if I want h to get closer to 0, a way that we write it out is writing it as a limit, and it's using this notation here. This is pretty much the only time we will be using this notation, so it's really important that you know what it looks like and what it means. So when we write lim means limit, and the bottom number tells you h is getting closer to 0. Okay, so the way that we say this symbol is the limit as h approaches 0. And we're doing this for this particular thing. So that was the gradient. Or the formal way of writing it is this. So remember we're talking about derivative, gradient is derivative. So f dash x we can write as the limit as h approaches 0 of f of x plus h minus fx over h. So that's the formula that we use. This method that we're looking at the moment is called differentiation from first principles. Okay, it's sort of like the core of what we need to know about differentiation. Okay, so here's an example here. But before we do that, let's go back to that diagram that we looked at before. So this one, let's go back with the value of h. So now we know what this value of h means. So if I make it bigger, then what I'm doing is I'm actually changing my secant. Okay, so if I have h equal to 2, then the other value I've got there is going to be 3, 9. Okay, you can see that there. All right, so 3, 9 is up the top there. So as I bring h closer and closer, okay, we can see that the gradient is getting flatter and flatter, and you can see that the line is becoming closer and closer to the tangent. But the problem with GeoGebra is if you go to 0, it doesn't recognize the gradient there. Okay, so that's why you can put a tangent on, and you can see as it's getting closer and closer, you can see that the slope is getting closer and closer to the value that we want. You can do that with any other value, so you can play with this. This one's quite useful. So you can see the gradients, so you can see the secant, and then it's getting closer and closer to 0. Let's get back to the example. So this one, differentiate this by first principles and show this result. So if the question ever asks you to do by first principles, it means that you have to use this formula. Okay, so you have to use this formula in order to work it out. So let's start with our formula. Fx is this. F dash x, sorry. F dash x is the limit. That was the formula from before. So what we need to do is we need to work out this value and this value based on the equation from above. So fx, we know, is x squared. So that's the second number. F of x plus h means that we replace x with x plus h. So that becomes x plus h all squared. And you can see that's what we've substituted into the next line. With that substitution, we're going to expand and simplify. So when we expand, we can cancel the x squareds, and then we've got 2xh plus h squared over h. Okay, right there. If we factorize out the h's, then we can then cancel those h's. So we've got the limit as h approaches 0 of 2x plus h. And you can see now we don't have a h in the denominator, which means we can substitute h into this equation. So you can see the whole way down, I've put in this limit thing, okay, and that has to be there right until that last step when you make a substitution of x equals to h equals 0. So if you can't substitute h equals 0, you have to keep writing this thing out. And when we substitute h equals 0, we end up with 2x. So what that means is that if I have a parabola, y equals x squared, then the gradient at any of those points is going to be 2 lots of the x coordinate. So that's the first part of the question. The second part of the question was to show that f dashed 3 equals to 6. So right now we've got f dashed x equals to 2x, which I've written here. So then if I'm putting in 3, I'm replacing x with 3, so 2 times 3 is equal to 6. So we've got that result. Here's another example. This one gets a little bit trickier. So the more things that we have in our function, the messier it does get. So starting with that equation, the formula that we had from before, we're going to work out the components. So we know fx is here, and fx plus h is when we replace all of the x's with x plus h. So we've got x plus h minus 2 lots of x plus h all squared. So when we go to expand that, we'll end up with this result here. Okay, this is where your algebra needs to be very, very good. So when we put all that together, the x's will cancel, the 2x squareds will cancel, and then we're just left with h minus 4xh minus 2h squared. Still over h, okay? So the denominators, you need to make sure you remember the denominator all the time. H is a common factor, so we can take that out. And we've got 1 minus 4x minus 2h left. The h's will cancel. And now, with no denominator, we can now substitute h equal to 0. So then we end up with 1 minus 4x. And that's the solution. So the derivative, okay, for fx equals x minus 2x squared is 1 minus 4x. Now, when we're doing this first principles, what you'll notice is this thing here, the minus fx bit, should always cancel with stuff in the beginning. Okay, so if this last bit, the minus fx doesn't cancel, then you may have made a mistake in your expansions. So you'll need to go back and check it. So ultimately, when you end up with all your cancellations, your numerator should end up with all h's so that you can cancel those out. Okay, there are other instances, other derivatives where it may not cancel, but it needs to be written in a way such that you can make a substitution of h equals 0. So they do, in these ones, they do need to cancel. What we can now do is, if we know how to differentiate and we know how to find the gradient, we can actually go then and find equations of tangents. Okay, so we can actually go and work out what is the equation of that particular line. So we have something about the gradient and we know a point that we're going to be working with. So what we can do is work out the gradient by substituting in x equals -1 into the equation from above. So f dashed x is 1 minus 4x. So if I substitute x equals to -1, I'll end up with a gradient of 5. We have a gradient, we have our point. So what we can now do is put these values into the point gradient formula. Okay, remember when we did this earlier, I said this is going to be a really important equation, a really important formula that you're going to be using a lot of. So when we substitute the values in, y minus -3 equals 5 gradient bracket x minus -1. So we'll simplify that and expand the 5 in, and then we'll bring the 3 across, subtract that, so then the equation is y equals to 5x plus 2. We'll do a lot more with tangents and normals a little bit later, but this is just showing you where we're going with it. For the most part, this exercise is really about the algebra, working out what the derivatives are using the first principles.